So everything up to this point has been fairly qualitative in looking at phase diagrams, looking at plots, being able to read things off of them. But we'd like to understand why they're shaped the way they are. Why is it always solid at low temperature and high pressure? Why is it liquid at low pressure and high temperature? And what gives us the tools to do this is to look at the Gibbs energy of pure substances and how they interact. And so if we're thinking about phase diagrams, one question we have is, what tells us which phase is stable at a given temperature and pressure? And I've kind of given away in the title here, the thing that we need to be thinking about is the Gibbs energy. Because at constant temperature and pressure, the phase with the lowest Gibbs energy, right, the most negative value, will be the most stable phase. Now, why is that going to be the case? Well, if we write out a delta G for the transition, right, whatever transition that is, solid to liquid, liquid to gas, gas to solid, whatever, that's going to be equal to the Gibbs energy at phase 1 minus the Gibbs energy of phase 2. And delta G is only going to be less than 0. Whatever leads to delta G less than 0 will be spontaneous, right? And that's just based on what we've looked at already. Just like that's the property of delta G that makes it so useful. And so whatever G is smaller is going to lead to the system is going to spontaneously go in that direction. So for a given temperature and pressure, it's the Gibbs energy that's going to determine which direction things want to go. So we want to go to the lowest value of G. And usually we'll think about molar Gibbs energy, right? So if I'm going to write these all as molar values. So we want to think about how does Gibbs free energy change with respect to temperature and pressure, right? Those are the variables we're thinking about. So we can say, okay, what is the change in G with respect to temperature if we're holding pressure constant, right? So if we're thinking about going just along one axis of that phase diagram. Well, from the last chapter, we looked at this, right? We looked at dG equals SDT minus SDT plus VdP, right? That was a formula that we derived, and so we can say that dG dt at constant P is equal to negative S. And we'll just put everything as molar values here. Okay, so the slope of a line where we're looking at G versus temperature, if we're holding pressure constant, is equal to entropy. And now what does that mean for us? Well, what that means is that we make a plot of Gibbs energy versus temperature. So we plot the molar Gibbs energy. We will see a negative slope to this, and that negative slope is equal to the molar entropy for that substance. And what we'll see is, that should be a straight line. What we'll see is that we'll end up with, it's not quite that pronounced, we'll end up with places where different phases, so this would represent, say, solid down here and liquid over here, we'll end up with places where these lines will intersect. So this is looking at G versus temperature for a solid. We'll see a negative slope, and liquid will have a larger negative slope. Why is this? Well, this is something we've already talked about. The entropy, the molar entropy of a liquid is greater than the molar entropy of a solid. And so if we're thinking about the Gibbs energy of a liquid, it's going to have a higher slope because it has a higher S value, a higher entropy. And where these intersect, this is what we call the boiling point, right? This is where we have equilibrium. Where the delta G for the transition is equal to 0 because the G values are equal to each other. And so this is a general trend that's going to be true for gases as well, right? As we go to even higher temperatures, we're going to have an even, let's see, I didn't give myself enough room on here. We're going to add another phase down here with a much larger slope, and this is our gas, right? Because the largest entropy is in the gas phase. And so we're going to end up with a third point here that's going to represent, right, this is, oh, that's not the boiling point. This is the melting point. And gas to liquid, this is the boiling point. I have this written wrong in my notes. Okay, and so we can see sort of as we increase temperature, we can see why we would expect to go from solid to liquid to gas, because these lines, these slopes, are going to be different for each one because the slope is based on the entropy, right? And the reason that we start with solids, say, at the lowest is what we have to remember is that there's also an intercept to this, right? What we can think about is G equals H minus Ts. This is the definition of the Gibbs energy. And so we're looking at just this part, the negative Ts, as we increase temperature that has the slope based on S. But what also matters is H. And so a gas is going to have the highest entropy value, has the highest sort of internal energy, right? H is U plus PV. Whereas a solid will have the lowest internal energy, lowest enthalpy value. And so we will tend to favor solids at low energies or low temperatures, we would say. And as we increase the temperature, we're going to go towards liquid and gas. And so that explains the temperature behavior we see on these phase diagrams, where we start with solids at low temperatures, go to liquids in the middle, and go to gases at higher temperatures. Now, depending on what pressure we're at, we may skip the liquid phase, right? And we may go straight from solid to gas if we have a sublimation. In that case, right, the solid and gas will intersect before the liquid even becomes relevant. But that's looking at G as a function of temperature. In the next video, we'll look at how we have trends in pressure and what affects that.